Now that we've seen a couple videos on vectors and some properties and how to compute certain aspects of vectors, like their components, and how to represent them like in component form, or maybe using a linear combination of standard unit vectors. Most of this took place in 2 dimensions. At the end of the last video, I started to introduce vectors in 3-dimensional space, but now we want to kind of take that step and get fully comfortable working in 3-dimensional space. So first, let's do kind of a little bit of maybe review, maybe not review, it's fine if it's not review, about kind of how do we visualize and go about working in 3-dimensional space. So let's first look at a coordinate system. So maybe drawing a coordinate system. Okay, and so there are many ways you can draw your coordinate system in 3-dimensional space, but it must behave, or it must abide by the right-hand rule. So your coordinate system must follow quote unquote right-hand rule. Okay. And so let's look at a few examples of correct coordinate systems in 3-dimensional space. Have X, Y, and Z here. And so again, you can think of X coming out of the screen, and you can think of Y and Z being the 2-dimensional space that makes up your screen. So Y and Z are actually on the screen, and anything spanned by Y and Z is on the screen, but X is actually the 3rd dimension coming out of your screen, right? And so the negative X direction is in your screen, like going back past your screen. And what you can notice here, so let's look at another one quickly. Another one is I can take a rotation of this coordinate system and express it as now the x-axis is horizontal, the positive y-axis is going into your screen, and the z-axis is on your screen in the vertical direction. Okay, notice this is a rotation by 90 degrees of the first coordinate system that I drew here. And these are fine representations for the coordinate, for the 3-dimensional coordinate system, because this follows the right-hand rule. And so let's learn what the right-hand rule is. If you take your hand and point it in the direction, so let's draw a hand here. Okay, so it's humongous pinky, but that's all right. You take your hand and point it in the direction of the positive x-axis and curl your fingers towards the y-axis. The z-axis should be pointing in the direction of your thumb. So if you can imagine this hand curling their fingers to making a thumbs up sign, like this, where their hand started in the direction of the positive x-axis and they curled their fingers towards the positive y-axis. Their thumb should point in the direction of the positive z-axis. This must be the case for your coordinate system to be correct. And this is what the right-hand rule is. So you can always check this, right? So an example of one that fails So let me list out the steps here and then show you an example of one that fails. So place hand in the direction of the positive x-axis. That's the first step. Next step is to curl fingers in the direction of the positive y-axis. And then your thumb tells you the direction of the positive z-axis. So here's a recollection of the right-hand rule here. And so one that fails, so an example that is not good, would be if I took this and just flipped x and y, right? So now what would be positive x's into your screen, and then y, the YZ plane is your screen, okay? If you take your hand in the direction of x and curl your fingers towards the positive y-axis, your hand has to be upside down. Your thumb would have to be pointing down, and then your fingers are out like this. And you would have to curl your hand in this direction, because you would be then giving a thumbs down, right? If you took your hand in the x direction, sorry, that was misleading that I drew them on that side of the hand, right? You would have to curl your fingers in this direction to get it. So x is into your screen, so I'm poking my hand into your screen and curling my fingers towards the y-axis, right, which is back in the screen. And my thumb is pointing down, which means down here, this is what should be positive z-axis, which means since my thumb was pointing in a different direction than what I indicated the z-axis to be, that means this coordinate system did not work. And so I can't express my XYZ axis in this way. Okay, so there's an example of one that doesn't work. These are probably the two most common representations. I will probably go between these interchangeably. I might favor this one here. I kind of like this one because the octant where X, Y, and Z values are all positive is closest to us, and maybe it's easiest to see what's going on in the positive octant. But okay, I think that's enough about coordinate systems. Let's quickly recall, we're going to need it here. Let's recall the distance formula. But for 3D space, for 3 dimensions, okay? So if we have, let's draw our coordinate system, x, y, z, and let's say we have 2 points. P, which is x1, y1, z1, and Q, which is x2, y2, z2. Sorry, I'm running out of room. Then what is the linear distance between these 2 points, right? There's some distance here. We can recall that the distance formula, which now may look strangely familiar to the formula for magnitude of a vector between 2 points. The distance formula is given by x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared, right? So here's our formula for finding distance between 2 points in 3D space. Okay, you basically just add the z component, right? Okay, so next I'd like to actually talk about equations in 3-dimensional space. and being able to graph equations. Like, what does a graph look like in three-dimensional space, right? So what do equations in two-dimensional space look like? Like, what are equations in R2, right? This means, you'll recall, this means the real numbers. So this is the real numbers squared. So the real numbers times the real numbers. This is the XY plane. Okay. And so equations in R2, usually they're represented as y equals f of x. They don't always have to be. They can be represented like f of xy equals a constant, right? An equation in R2 represents a curve, right? This is like y equals f of x. Or, you know, like we represent circles as something in this form here, where it could be like x squared plus y squared equals r squared, right? So these are equations in R2. What are equations in three-dimensional space? Equations in R3, right? And now R3 is three-dimensional space, so it's like R times R times R, right? Equations in three-dimensional space. So let me say one more thing about equations in two-dimensional space. An equation represents a curve, right, in two-dimensional space. Now, an equation sometimes can look like z equals f of xy, or something like f of xyz equals a constant here. These now represent a surface, where the analog in two-dimensional space was a curve, and higher one dimension up, the equations represent surfaces. So for example, in three-dimensional space, we could now have a surface. Maybe you can imagine like a sheet, like you're holding a bed sheet and you shake it and it's making some sort of like wave, right? You can represent that surface in three-dimensional space as an equation in x, y, and z. And so, you know, maybe we take this sheet here and we shake it and give it a wave. And now this is like z equals f of xy. And so equations in three variables in x, y, and z are going to now represent surfaces in our Euclidean space. Whereas, again, the analog is equations in two-dimensional space represent curves, equations in three-dimensional space represent surfaces. So I want to go through a list of basic equations in R3 in three-dimensional space. So let's look at equations for planes parallel to coordinate planes. What are coordinate planes? There are three coordinate planes. There is the xy plane, the xz plane, and the yz plane. Okay. So if we draw x, y, z, we express our coordinate system here. Let's draw the xy plane in red. The xy plane is simply what our two-dimensional space normally is, right? It's just the xy plane. But now you can imagine this being flat, right? Because y is horizontal on your screen and x is coming out of your screen, right? This is the xy plane. Let's look at the xz plane, right? The xz plane is now where you exclude y. here, and we have the XZ plane like this, which would be kind of upright, if you will, right? Because Z is vertical in your screen and X is in and out of your screen. So it would be this upright plane, right? And then the YZ plane, so let me write here, this is the XZ plane. And then we have the YZ plane, which is just completely in the screen, right? No in and out of the screen right now. In blue here, this would be the YZ plane. And we call these the coordinate planes because they completely determine your coordinate system here. And we want equations for planes that are parallel to these. So you take like one of your coordinate planes here. And so for like the XY plane, you can imagine we could shift it up Z units, right? If you can imagine we're taking this flat plane and shifting it up, right? Or we could take this green, the XZ plane, and shift it left and right, but in a parallel fashion here. Or with the YZ plane, we could shift it closer and farther to us. Okay, and we want equations for those. So if we have a plane parallel to the XY plane containing the point ABC, this is expressed as simply Z equals C. And what does that mean? This equations give us restrictions for possible values, right? These are X, Y, and Z values. Equations give us restrictions for possible values. When I see the equation Z equals C, this tells me I have no restriction on X, I have no restriction on Y, but Z can only be one fixed value. So what does that mean? When I look at a picture here, I have X, Y, Z, and somewhere I hit the height. You can think of Z as a height, right? If X and Y is a flat plane, meaning the XY plane corresponds to Z equals 0, then we get up to some height here. The equation Z equals C means we've taken a parallel copy of the XY plane and shifted it up or down C units, right? And this makes sense in terms of viewing our equation as basically rules and restrictions for what possible values our surface can take, right? Because here, notice X can be anything. I can go to positive and negative infinity in the X direction. I can go to positive and negative infinity in the Y direction, but I'm stuck at this level, right? I'm stuck at the level Z equals C, right? I'm restricted by this value. And so that's why we have this plane here. And so you can see, what about something parallel to the XZ plane containing the point ABC, right? So you can imagine now X and Z have freedom and Y is restricted. So this is given by the equation Y equals B. This is now X, Y, Z, right? Now X and Z have the freedom, but somewhere we have the value Y equals B. And that's our only restriction. And it's something parallel to the XZ plane. So we've kind of, again, X and Z this equation tells me nothing about x and z, which means there's no restrictions on x and z, right? The only thing I require is that I am in this slice at y equals b, and that gives me some plane. Okay, and we can do this one more time to get an equation for planes parallel to the YZ plane. So parallel to the YZ plane containing the point ABC is going to be, and maybe you've guessed this by now, the equation x equals a, right? This gives us parallel transformations of the YZ plane. So I'll draw one more picture here. X, Y, Z. And this one might be a little harder to visualize based on how I've drawn my coordinate system here, right? But you can imagine maybe A is a negative number. So we go back to this value negative A, right? Or not negative A, but A here, right? Because that's into your screen is the negative x direction, right? And so the plane x equals a is going to be, it's a parallel copy of the YZ plane, which is your screen, but it's shifted back a units. And so if a was a positive number, it would be shifted towards you a units, right? So there's a first set of examples of surfaces in three-dimensional space. There's another really important one. Some would argue maybe the most important, and that's a sphere. Okay, so let's see how can we represent a sphere using an equation. So for a sphere of radius r, centered at the point ABC, is expressed algebraically as x minus a squared. It's very similar to a circle, but in one dimension higher, right? Because it's a set of points at a fixed distance from another specified point. So this is x minus a squared plus y minus b squared plus z minus c squared equals r squared. Okay, and so we can draw that here as x, y, z. Let's say here's the point ABC, okay? And then a sphere is something of a fixed distance. It's not a very good picture. Let's look at a bigger picture so it's easier to see what's going on. So x, y, z. Let's say this is our point ABC. And then we're at a fixed radius r, but this is a sphere, so it's a three-dimensional object. So you can kind of imagine that this is the front of the equator here in black, and then the dotted black line is like the back side of the equator there. Okay, and this is a sphere centered at the point ABC with radius r. Okay, and there's a handful of other types of graphs and equations in three-dimensional space. There's a pretty generalized name, so in general, and we'll study these later. So we'll study what are called quadric surfaces. So we'll take a look at quadric surfaces in a few sections. We want to build some more notions of vectors first before we really get into studying quadric surfaces. But I want to give you a quick example of a quadric surface. And then I want to close this video with just kind of a summary of vectors in three-dimensional space. So let's look at kind of examples of graphing other types of equations. Graphing other types of surfaces in three-dimensional space. Okay, let's look at two examples. Here's the first example. Let's graph the equation given by x minus 4 times z minus 2 equals 0, right? And we want to know, okay, what surface is this equation representing? And there's two examples I want to show us for now, because there's two general methods that we can do. If you have an equation where it's things factored like this, where it's like one variable in this factor times another variable in this factor equals something, especially 0, you can do this. We can say, well, this is only true when two cases. This is true when x minus 4 equals 0 or z minus, z minus 2 equals 0. Well, if x minus 4 is equal to 0, then we know x equals 4 or z equals 2. Okay, so we've simplified this equation into two equations. Like it's a couple of possibilities, right? It's either x equals 4 or z equals 2. So what does that mean graphically? So we have x equals 4 or z equals 2, right? Graphically, we have x, y, and z. Well, if x is 4, that's 1, 2, 3, 4, we learned that x equals 4 is a plane that's parallel to the YZ axis, but at the level x equals 4. So we can draw a plane parallel to the YZ axis all the way out here, like 4 units out of your screen, right? Or we can have z equals 2. So we can march up 2 units on the z-axis and then draw something parallel to the xy plane at the level z equals 2. And you notice these intersect, like somewhere in here, these planes will intersect, right? And so we have kind of like a crossed section of planes here that are both parallel to coordinate planes. So that's then this picture here is the graph of x minus 4 times z minus 2 equals 0. I want to give one more example. This was the second example. Let's graph x minus 2 squared plus y minus 1 squared equals 4. And so if I gave this to you, so remember, I want to graph this in R3. If I told you this in 2 dimensions, you would say, okay, well, that's in the xy plane. That's a circle of radius 2. It's a circle of radius 2 centered at the point 2, 1, right? So you'd say, okay, cool, 1, 2, 1, circle of radius 2, something like this, right? And in 2D, you would be correct, but we want a graph of this in 3D, right? And so we know that this should be something circular of radius 2. But now we have the z variable to think about. But if you notice, this graph tells me nothing about the variable z, which means it has no restriction, right? Remember I said equations in three-dimensional space, or equations in general, tell you your rules and restrictions for what possible points this surface can include, right? And so what this is telling me is I have this two-dimensional restriction. This x minus 2 squared plus y minus 1 squared must equal 4, but I have no restriction in the z direction. So when I want to draw a picture of that, x, y here, z is the height. Well, I know in the xy plane, I have the restriction that x minus 2, so I come to the point 2, 1 here, and it's a circle of radius 2. So it looks something like this here. It's not perfect, right? But you can imagine that's a circle of radius 2, and I have no restriction for the height. So I can extend this circle infinitely up and infinitely down in the z direction. And if you can imagine doing that, no restriction in z, this gives me a cylinder. The graph of x minus 2 squared plus y minus 1 squared equals 4 is a cylinder of radius 2, right? This distance here is 2. So it's like an infinite Pringles can, if you will. And so I wanted to go through these examples so we can start to see what surfaces are represented by what equations. And again, we'll touch more generally on quadric surfaces in general, but I wanted to give an idea for some important ones and some of the first ones that we'll start to look at. And it also helps us get an idea of picturing and working in three-dimensional space, which is very, very important in multivariable calculus. Okay, so lastly, let's just kind of summarize what we learned about vectors in two-dimensional space, but now let's summarize it written in the language of three-dimensional space. So here's vectors in 3D space. Okay, so we have a vector v, whoops, in component form, which can be written as x, y, z. This is component form. We could also express vectors using as a linear combination of standard unit vectors, which this would be in 3D space would be xi hat plus yj hat plus zk hat. Okay, this is standard unit vectors. Okay, let's recall what the standard unit vectors look like here just for practice. We have x, y, z. We have I hat in the x direction, which is of length 1, right? This is the vector 1, 0, 0. We have j hat, which is the vector 0, 1, 0. And then we have k hat, which is the vector 0, 0, 1. Okay. What else do we know about vectors? We know the vector between 2 points. So if we have the vector between P, which is the point x1, y1, z1, and Q equals the point x2, y2, z2, right? This is given by V, which we also express as PQ as x2 minus x1, y2 minus y1, z2 minus z1. It's the terminal point minus the initial point, but you take these differences component-wise, right, as we can see here. Let's remember some properties here, and then we can wrap it up. So we have scalar multiplication. Abbreviate here. So if we have a vector, for these properties now, let's say I have a vector v, which is x1, y1, z1, and another vector w, which is x2, y2, z2. Not to be confused with the points on the previous page. These are now vectors, right? P and Q were points. These are vectors. So let's think about these as vectors now. Scalar multiplication of v is the vector kv, right? Which is k times the vector x1, y1, z1, which is the same as kx1, ky1, kz1. We have vector addition and subtraction. I'll just write addition right now, right? If we have v plus w, this is the vector x1 plus x2, y1 plus y2, and z1 plus z2, right? Subtraction is defined in a similar way here. And the last two properties I want to remind us of, but just record them in the three-dimensional setting, are magnitude and unit vectors in the direction of a given vector. So remember, what's the magnitude of a vector? So the magnitude of v is given by the square root of x1 squared plus y1 squared plus z1 squared. Remember, v is this vector x1, y1, z1. And so the magnitude is the square root of the sum of the components squared. And then a unit vector in the direction of v is as follows. We say u is 1 over the magnitude of v times v, which, if you will, is x1 over the magnitude of v, y1 over the magnitude of v, z1 over the magnitude of v. And if you'd like to express this even more lengthy, purely in terms of components, it's x1 over square root x1 squared plus y1 squared plus z1 squared, y1 over square root x1 squared plus y1 squared plus z1 squared, and z1 all over square root x1 squared plus y1 squared plus z1 squared. Okay, so here was a quick recollection of our properties and notions of vectors, but now kind of purely in the three-dimensional setting. And you may be wondering, you know, we've talked about addition and we've talked about scalar multiplication, but we haven't talked about the multiplication of two vectors yet, right? Like take one vector times another vector, if we have that notion. And in fact, we have multiple notions of vector multiplication. There's the so-called dot product and the so-called cross product. And in the next lecture, we'll be taking an in-depth look at both products and a lot of their properties and applications.